Sorry. And anyway, so I found out, talking to people, I knew one person there, Rick and Dolores Hill. Well, it was two people, but I knew them, and they worked at the Lunar and Planetary Lab. And he told me that, you know, NASA gets a lot of their instruments for their spacecraft from universities. They build them. The scientists at the university are usually the people that propose those instruments, and they get a team together and build them. So I didn't know that. And then I found out that the Lunar and Planetary Lab had a team building a camera for a Mars lander. It's called Mars Pathfinder. It used a space-qualified CCD from a previous mission that was going to Titan, and that was the DISR instrument. That was also made at the Lunar and Planetary Lab. There was a lot of contribution from Germany because they developed the space-qualified CCD and the readout electronics. The rest of the camera was built in Arizona. So I started as a student working on helping with assembly while I was going to class. And I did some design, test equipment, built stuff. Later on, they hired me in as a test engineer. So the camera that we're about to talk about for the Mars Pathfinder was actually designed by Lockheed Martin. And the parts were all made at U of A. The CCD and readout board was designed and built by the Max Planck Institute of Aeronomy in Germany. And they sent that stuff over to us. I learned an awful lot about testing requirements for Mars-bound instruments. You've all heard that it's really cold on Mars. Well, it's really cold on Mars. So we have to test stuff beyond what they think the camera is going to experience. They thought the coldest camera would get would be minus 90 C. So we had to test it another 20 degrees colder. So we went to minus 110, which is minus 166 F. And then we had to test it to 60 C, which is very hot. That's 140 degrees F. That stresses all the electronics in there and gets rid of any infant failures that may damage the instrument in the mission. We also had to withstand a radiation dose of 1,500 rads. And there were vibration and shock requirements. But because this mission was going to land with airbags, there was also a G-load requirement. Those impacts on the airbags, we had to be able to withstand 25 Gs on the camera. So, and this is the airbag in a very large vacuum chamber in Ohio that NASA has. And they're dropping it on this simulated Martian surface with a whole bunch of lava rocks and sharp stuff on there. And they did this many, many times. They kept turning the bags and they kept repairing them and adding more layers of stuff, and they eventually got it so that they had confidence they would survive the impact. The reason they did this was when they land with rocket engines, the rocket engine exhaust contaminates the site. So if you're going to dig up dirt and try and look for volatiles and things like that, well, you're carrying a whole bunch of stuff with you when you land. You don't know what's native and what's you brought with you. Also, they thought this would turn out to be lighter and less critical than landing with rocket engines. It didn't turn out to be that much lighter. So this was also the first mission to have a rover. And so this was actually getting a lot of attention. And it was going to give us the first surface image of Mars after 20 years. So this is the camera. It was called the IMP, the Imager for Mars Pathfinder. It's a stereo camera. So every time it takes an image, it gets an image on both eyes. And so the way it works is, light comes in this eye, bounces off a mirror, goes through a filter wheel here, goes through the lens, bounces off another mirror, and goes up to the CCD. The other eye does the same thing, goes up to the same CCD. They had two images on one CCD. That's rather tricky to do without a lot of bleed over from each image, but there was a lot of careful baffling done to make that work. This was designed in 1994, so this is the sort of thing that's the state of the art in '94. This is what the camera actually looked like. It traveled there with this mask all coiled up into this canister. And when they landed, after they unfolded the pedals and got the lander straightened up, they would pull a pin on it and it popped up. So it also had 12 filters for each eye, and so they had lots of different filters for looking directly at the sun, so they could measure the amount of moisture in the atmosphere, measure the characteristics of the dust in the atmosphere. That's where they characterized the size of the dust in the atmosphere. So that was a big deal for a camera. The Vikings had, I think, 7 or 8 color filters for their cameras, and we've had 24. So this is the cast of thousands at JPL that are folding up the pedals for the last time to get it ready to be packaged up to go on the rocket. And there's the camera with the mask stowed on top of the lander. There's the rover. Now when this thing's all folded up, it's tetrahedron. So it's going to land on one of its 4 sides after the airbags deflate. It has accelerometers inside, and it can tell which way it's laying, and it powers each pedal out as needed to right itself, put it on its base, and then pull the rest of the pedals out. So I got to go to Florida and see the launch. That was fantastic. We were in a hotel on Cocoa Beach, right on the water. We were on the 4th floor so we could see over all the trees to the launch pad, although we were like 6-7 miles away. This is a stock photo from a NASA site. I tried to take pictures with a telephoto, but they're on film somewhere in my thousands of pieces of film. I have no idea where they are now. Anyway, so I was at LPL working on parts for the Mars 98 cameras. It's the next mission I'll talk about. When the Mars Pathfinder landed, and I got to see all the images as they came down. They had a big projector, which a digital projector was a big thing in '97. Okay, and this is the medieval years of the internet and computers. So a big projector that made like an 8-foot square image was a big deal. So we could just go in there anytime. They preempted all the classes, canceled everything, moved them out of the rooms, and all that big auditorium did all day was show images that came down. So it was really great. Just go in there at any time and sit down and just watch them pop up on the screen. This is a mosaic produced from all those images, a color mosaic of the landing site. It's wrapped around, it's full 360 degrees. It takes about 150 images to make, for each color, to make this image. The field of view in the camera is 14 degrees square. We took every 12 degrees as you went around, so it takes 30 to go all the way around, and then 4 to 5 vertically to scan up into the sky a little bit and down to the edge of the lander. The other thing that Peter did that was, I think, really helped the popularity and the notoriety of this mission was he put all these images up on the LPO website. Until then, people would hold their images close and they would dole a few out to the press, to let them see. But the public didn't really see anything until papers were published 6 months later. He took the images after they'd been through the calibration pipeline, they're all cleaned up and, made as good as they could be. He put them up on the LPO website. The server was swamped. So the local SEDS club, Students for Exploration and Development of Space, they mirrored the LPO website to help out. Their server got swamped. Now you got to remember, this is '97. People are on dial-up. Okay? They're downloading these images on dial-up. And so they called up Sun and they said, can you give us another server? We're just swamped. So Sun gave them their top line, brand new server, gave it to them. They configured it, they plugged it in, they turned it on, set it to serve. The utility went to 100% and stayed there for 6 months. The sun guys would log into the server and it says, why is your server so slow? And then they look at the utility utilization, it's 100%. And then they make a plot of it, and it's 100%. For just months, they couldn't believe it. Anyway, so this got a lot of people's interest. Okay, now we're ready for our first stereo 3D. Can people see it?
Yeah.
Now, the first time I saw this, I didn't realize where Mars Pathfinder landed was an alluvial plain or a float plain from a large flow of water. And there are undulations in the ground from that flow. And so if you look, there's a little valley right here. There's a ridge running across here. There's a valley we can't see over there. There's a little bit of it you can see there. There's another ridge here, and the next thing you see, this is like a kilometer away. So I thought this was just one smooth surface out to the hills, but not at all. That's one of the utilities of being able to see in 3D, just the way your mind tells you what's going on. Oh, sorry. Here's two more 3Ds. These are near field. This one is called the super resolution. It's in color. At least it looks like it's actually in color. So you see, I gotta be careful with this, because this remote. This was produced by Timothy Parker at JPL. What he did was he realized that every time we took an image, because we did several pans, every time we did an image and took a pan, the camera was very slightly different. There was some backlash in the gearbox and everything, so he took all the images of the same spot and did some computer manipulation and extracted even more resolution out of the images than the camera was capable of, nominal. And produced a color amplet, which is just amazing. And so you can see here's the edge of that ridge, the rocks sticking up, and you see the rocks are gray and the dust is red. Dust is iron oxide, the rocks are lava rocks, they're basalt. And then here's one with the rover in the corner of the image with the rock they call Barnacle Bill. This is another 3D pan of a little closer up to the lander, so you're looking more down, but it's just, the ground is all rocks. You know, the guys that were worried about hitting sharp rocks with the airbags, well, they had reason to worry looking at these things. Anyway, even the post office got involved in this thing. They took that first image of the rover still on the pad, Sojourner rover, and made a stamp out of it, and I had to have one, so I got one. Then my surprise was I watched this movie called The Martian, and the imp shows up in there. Only it's not quite the imp. Now I gotta admit, they did pretty good. The camera head, this is the real camera, the camera head looks really good. I would be hard to pressed to tell it's not the real thing. The base, when you see it in the movie, looks really good. The mask, the mask is not this mask. And it goes up and down. Every time the camera powers up, it shoots back up out of it. It's not the real. This was a deploy once and that's it. And so this is a picture of the Pathfinder taken by the rover. So that's the way you should have found it. It would have been standing up on the mast from, years and years. Go ahead.
The mast in the picture on the left looks kind of flimsy, and it just seems to me that even though the Martian atmosphere is thin, any wind would have caused some shaking or vibration which would have blurred the pictures.
Well, actually the mast is quite stiff. The longerons are all epoxy glass rods. You see these little cross members here, they're a little bit curved. They're epoxy glass rods. They're trying to straighten out. What you probably can't see is there's little stainless steel diagonal wires going across each one of these bays on each side. Those battens are trying to straighten out. They tension those stainless steel cables. And so the mast is actually quite stiff. The first resonant frequency of this 3-pound camera had 30-some inches off the ground was like 10 hertz. It's pretty high.
So they're all under tension?
They're all under tension. So I've deployed the mast and stowed it several times. What you have to do is you grab the camera head and you start twisting it and you buckle it. And once you buckle it, the longerons become a spiral. And then you slowly turn it and push it down, and the spiral works its way down until eventually they're all spiraled. All the battens straighten out, and all the guide wires become little loops that you have to very carefully make sure to get down in the canister without sticking out anywhere or grabbing anything. So stowing it takes 3 people, and it takes about 20 minutes. There's a little pin right here. There's a pin puller in the base of the canister that has a pin that goes through the hole in it, and it holds it down with quite a bit of force. The pin puller pulls it out and it just pops up. And I have to say, the job they did on the lander itself was really good. I mean, this is that same mosaic, but redisplayed as a circle. And then the center part is a model, so don't pay attention to that. But, you know, the pedals and the ramps and everything, ramps are gone. I don't know why they're gone, but, you know, it's been 30, 40 years, so maybe they've pulled in, but here's the airbags. The airbags are really well attached to the pedals. I really don't think they would be gone. But, you know, this is a move, okay? I'm being really picky. Yeah, but I mean, it looks really good. If you know, show me this pedal and that pedal, and say, yeah, they're really good. Anyway, so the next mission, Peter worked it so that we delivered our instruments for one mission. We immediately started working on another mission. We got another proposal for another camera, actually 2 cameras, for the Mars 98 polar lander. So we got the project, and heritage is a very important thing in spacecraft design and construction. When you say, okay, you've got a successful camera that worked on this mission, and you want to build a copy of it, man, NASA's all over you. They love it. They say, okay, you didn't have any problems. You know how much it costs to build. You have all your drawings, all your parts. You've obviously made it once. You can make it again. So we were going to build a copy of the camera, only this time it's called the Surface Stereo Camera, the SSI. The other thing is, Max Planck designed and built a robotic arm camera for the robotic arm. This lander was going to land with rocket engines at the Mars South Pole, near the South Pole, and look for water ice. So they're going to dig into the ground. Well, the arm needs a camera on the end to see what they're doing and to see what they found. So the Germans came up with a really clever design for a very compact camera. And it included a focusing mechanism, which is a real first for a spacecraft camera. I mean, focusing mechanisms are on everybody's camera. Nobody thinks much about them. But for space, that's a very unusual thing to do. You only do it if you really have to. Well, they wanted to be able to focus on the ground. They wanted to be able to focus at stuff in the scoop and stuff right at the tip of the blade. And when they were at the tip of the blade, they were doing one-to-one imaging so they could see stuff the same size as the pixels on the CC, which is 23 microns. It's about a thousandth of an inch. So they could see a thousandth of an inch per pixel. It's kind of a crude microscope. But it was a monochrome CCD. So they asked me if I could design a set of color lamps to go in front of the camera that would let them take color pictures so they could tell what they're looking at. Is this basalt? Or is this iron oxide? You know, is it red? Is it black? Is it gray? What is it? So I said, sure, I'll do that. And I designed a set of lamps, and I tested them, and they failed. And I spent 6 months designing this set of lamps, getting them built, and they failed. And they failed. Every lamp burned out. I won't go into the long story, but I made some assumptions about expansion coefficients of some materials that I didn't really have data for. I thought they were like this other material, they weren't. So they broke all the balls. So I had to work some really long hours to get caught at, to come up with a new design. It was nowhere near as good, but it worked. It worked, and it survived all the testing. Just made me really, really appreciate conservative engineering, because you can't go out there and fix it. You get one shot, you get to build one piece, and it has to work, and it just has to work. So you got to be very conservative. At the same time, we were building parts for the SSI, So we got to go to the Lockheed Martin in Denver, deliver the stereo imager camera. This is the camera on the lander, corner of the lander deck. There's the robotic arm, and there's the robotic arm camera. You'll see more detailed pictures of this later because it comes back. There's the scoop, and when the scoop is rotated toward the camera, it comes about ½ an inch away from the face of the camera. And we could focus on material right on the tip of the blade. So that's how we did that. And this bulge on the front, those are the lamps. So again, I got to go to Florida for the launch. It was a night launch this time. Really spectacular. You think, well, am I going to be able to see the rocket? It lights up the whole sky. I mean, you're standing 5 miles away, and the whole sky lights up, and you see this brilliant exhaust come flying out of the ground. I mean, it's just, I got to invite my mom, her husband, and my sister, and a couple of her friends, and we had a great time. And I shot some slides, and they're in a box with like 1,000 other slides, and I can't find them, so.
At least they're positive.
Yes, and I'm pretty sure I still have them, I just don't know where they are.
Hey Roger, sorry. Are you in that photograph a couple slides back?
This one, yeah, that's me, before my beard turned green.
One on the front, the person in the front.
I'm right there. This is noticeable that you saw in the JPL photo, everybody wore a complete face mask. No exposed beards, you just had a slit. This is Lockheed Martin, a little more lax. This is before NASA got really serious about planetary protection. Because they would have, well, for later missions you'll find out, we're never allowed to go in there without a full suit with just our eyes showing, and that's it. Everything else had to be taped up. So, and covered. So that, I saw that picture and I said, oh wow, yeah, I remember those times. We got away with a lot of stuff.
We're in the later 90s now?
This March 98, we delivered in 97. So, actually it was end of 96 we delivered. So we delivered the next missions just before this one landed. Now this one was going to land differently than Pathfinder. So the sequence, the cruise stage detaches, the cruise stage detaches, goes through the heat shield in the atmosphere, chute pops out, they drop the heat shield, and when they get down low enough, they jettison the back shell on the chute, and then they turn the rocket engines on, and they go the last 5 kilometers, 3 kilometers on rocket engines. The reason they do that is they don't want the chute to end up on top of the lander, which inevitably it would. So this is the way it was supposed to come down. Now you notice the legs here are popped out. Well, when they're inside the back shell, they're all folded up into the lander. They actually go through the lander and stick out the top. So when they jettison the back shell, they cut some cables with cable cutters, fire protecting cable cutters, and the legs pop out. That will become important later. So I got to work on the Mars 98 Ops team. I couldn't work on Pathfinder because I was working on parts for the next mission. Well, I got to work on Mars 98 Ops. Went to the Science Ops Center, which is at UCLA in California. Got months of training, learned how to process images, and then landing day. You can tell by the looks on these faces, nobody's very happy. The lander did not phone home. After, I don't know how many days, 4 or 5 days, they finally sent us home and they said, well, if we hear from it, we'll call you back. After 3 months, they concluded it was gone. This is only 3 months after they lost the Mars Climate Orbiter to a navigation error. That's the famous units mismatch. This is the era of Dan Golden. His mantra was faster, better, cheaper. The old hands at NASA said, yes, pick any two. You don't get all three. You just can't say we're going to do it fastest, better, and cheaper. Doesn't happen. They just, anyway, so we got faster and cheaper. You can get better. There was a failure review board. They went through all the possible causes. They did a whole bunch of testing of the spacecraft, the spare parts. And they determined the most likely cause was there was a missing line of code in the entry descent landing sequence. That code resets some latches that tells the lander that the legs are not fully extended, i.e. you're on the ground now. Because the lander really doesn't know when it's touched the ground, except for the legs get pushed in. So it's running on its way down with the landing radar running, so it knows how far it is above the ground. When it gets to around 100 meters, the radar becomes unreliable because the outgoing pulse is still going on while the return pulse comes back. So all of a sudden the return pulse from the ground just disappears. So at that point, they should have reset those latches and then waited for the legs to be pushed in. But the lander thought it was landed already and turned the engines off. So it probably fell 80, 40 meters to the ground and crashed. Now they had 8 other things that could have happened, so that wasn't the only one. But so our next project was the Mars 01 lander. This lander was going to go to the Martian middle latitudes and look at compatibility testing, we called it, of the Martian environment for future robotic and human exploration. So they were doing things like testing the dust to see if it was acidic or, going to tear up your lungs if you breathed it. I mean, did they have to keep every bit of dust from getting into the habitat for a human because it was just going to destroy your lungs? So they didn't know. So they had a bunch of instruments that were going to test the dust. It had a robotic arm. It was going to pick up dust samples and put it in these instruments, and they were going to run chemical tests on it and all that stuff. Well, the instrument that was going to run the tests also they needed a microscope for it, so we built them a microscope. And this one had LEDs to light it up to take images again. And they also had a robotic arm with a robotic arm camera, so I got to design another set of lamps. This time, Nishia, a Japanese company, had developed gallium nitride green and blue LEDs, and they were really bright. And it also turned out they were extremely rad-hard, surprisingly for a consumer piece of electronics. We've taken some of these just commercial LEDs and given them 40 and 50 kilowatts. They drop in brightness by like 2%. You almost can't test it that good, so it's just amazing. It just happens to be the way they're made. So we had to qualify these commercial LED parts because there was no space-grade LEDs. It just didn't exist. So we had to buy 1,000